In this next video here, we'll be talking about this next example in terms of solving a systems of equations. The unfortunate part about this method is that it requires that we have three variables of three unknowns. Now, you could do this using two variables of two unknowns, but I feel like you're just going to get away from yourself and you're going to do more work than you have to. So this particular method of using matrices allows us to take the variables and hide them from the actual problem. So the first step that I'm going to do is convert this system of equations with x, y, and z into a single set of a matrix. So that matrix there is going to look something like this. So now the matrix we end up having is a set of brackets. I'm going to remove all of the variables from the equation. I'm going to remove all the additions and subtractions, and I'm just simply going to put them all into coefficients in this matrix. So I'm going to have a column here of just x coefficients. So it's going to be 1, then 3, then -2. I will then have a column of coefficients for my y. So that's going to be 2, that's going to be 7, that's going to be -4. The third one's going to be, again, the coefficients for my z, so -1, -3, and +3. I'm going to draw a dotted line to emphasize the augmentation, is what we call it, such that it's got this it's the full equation that represents the equal sign, and these three values here are just going to carry down untouched. So this is your first step in terms of using matrices to solve a systems of equation. Now, the problem with this, and just a few notes to make sure that you guys understand, if there wasn't a variable, say for z, maybe there wasn't a z in the second equation, we would put a 0 there in that placeholder. We don't want to lose any information, but we do want to make sure everything is representative of what we're looking at. So this particular system here, we're going to have to attempt to solve. Now again, remember the concept of solving a systems of equations is simply getting x, y, and in this case z. So our goal is to have some kind of correlation of x, y, z equals to something. That's what we're looking for. What is the x value? What is the y value? What is the z value? Now, if that's our goal, and this right here represents x, as does this, I don't want the x values in these two lines below it. Keep in mind, in the elimination method, we would eliminate one of the variables so that all we would have left is one specific variable. So really what we're going to do here is we're going to go ahead and talk about the operations we're allowed to use on this matrix, things that we're allowed to do to it. And then with those operations, we're going to have a goal. So we have the three main operations. I'm going to go ahead and go through those here. Operations. Operation number 1, or I mean, I'm going to label it A, operation A, because in the future steps, I'm going to actually write out steps of 1, 2, and 3, and I don't want you guys to confuse those steps with these operations. So there's operation A, there's operation B, and there's operation C. There are three specific operations. Now I'm going to write them in a very specific way. Keep in mind that these rows, each row represents an equation. So the operations that we do should feel like they're operations on a single equation in some form or another, or a manipulation of two equations. So the first operation we are allowed to do is swap two rows. So I'm gonna go row n swapped with, that's what that notation stands for. It's this one's being pushed over here, whatever's over here is so row n with row m. Now again, the example IE would be row 1 swapping with row 3. Now again, this might be a situation for when we want to do this, I'm not sure, but you'll notice over here again, swapping a row is simply like moving this equation down to here and this equation up to here. It doesn't change the math, it just changes the orientation of things. So we're allowed to make that first operation in here somewhere. I'll make note that I don't want to do that operation for this matrix, and there is a reason why, and you'll see here shortly. Operation number 2. Operation number 2 is simply taking a row, I'm going to call it row n this time, and multiplying it by some kind of constant. I'm going to call that constant k. So we're going to take some value, we're going to multiply it by the whole row, and we're going to store that back in that exact same row. So for instance, if I wanted to take this equation up here and multiply it by a -3, for no reason other than that I could. So again, taking row number 1, multiplying it by a -3, and then storing that back in row number 1. So I'm replacing that value in there. So this is very much like the method of elimination, where you multiply a row by, or you multiply an equation by a number on both sides of it, and then you eventually will add it to something else. And that's actually what the third operation is. Operation C is you're taking a row, you're multiplying it by a number, you're adding that to another row, and you're storing that back in that other row. So the important point to note here is that this one here permanently modifies row M and row N, such that it simply swaps the two rows. So again, it's like swapping row 1 and 2 here and flipping them around. The second operation permanently modifies one row. It takes row N, it multiplies it by a number, and it permanently replaces row N with that new thing. Operation C is kind of unique. Operation C is actually taking the steps of elimination all in one go. I am temporarily modifying R sub n by multiplying it by k. I'm temporarily taking that thing, I'm going to add it to row M, but that's when I'm going to forcibly replace permanently row M. So in this case, maybe something I could do here, and I'm going to go ahead and actually show this operation. My operation number 1 is me taking row number 1, multiplying it by a -3, adding it to row number 2, and storing that back in row number 2. So again, I'm taking this first row, this entire equation on top, I'm going to multiply every single value in there by a -3, I'm going to add it to row 2, I'm going to replace row 2 with that new thing. The row number 1 is not permanently modified. So when I go to rewrite my new matrix, and yes, every time you do an operation, you have to rewrite the matrix. So my row 3 is completely untouched, never touched it, didn't do anything with it, nothing's been changed. Row number 1 is changed, but temporarily. So row number 1 is going to end up being the exact same set of values. It's row number 2, the one that it points to, is the only one that actually changes. So let's go ahead and do this operation very carefully. I'm going to start off by -3 times row 1. -3 times row 1 is taking everything in this top row and multiplying it by a -3. So -3, -6, +3, and -9. Those are the four values there for -1 times R1. I'm then going to just rewrite row 2 right below it. Row 2 is going to be 3, 7, -3, and 12, and I'm simply going to take those two values and I'm going to add them together. Now, there is a way that you can consider doing subtraction, but again, I'm going to emphasize this addition here, and the addition of these two values make a heck of a lot, or things a heck of a lot smoother to deal with. So -3 plus 3 cancels out, that gives me 0. That's the reason why I chose that operation. I'll talk about it more here shortly. I get 1, this cancels out, that's a coincidence, and then when these two things I get 0, 1, 0, 3. So I'm going to go ahead and write 0, 1, 0, 3. That is the row 2 that is going to now be in place. Now, why did I pick that operation? Well, again, if the goal of solving this is to get x, y, and z, it means that I need a 1 here and these things to be zeros so that I know what x equals to. That's the idea, right? This is supposed to be x, this is y and z. But if I do that, then I get x equals to a number, and these two things have to be gone. The x's in the other two equations have to be gone so that I can very clearly say x is equal to this, and there's no other x's anywhere else. The same argument can be said for the y. Right in here, if I get this value to be a 1 and all the other values in that row and column to be zeros, then this becomes obviously y, and nothing else can influence that. And then lastly, if this and this are 0, and I have z equals 1 here, that means I know what z equals to without any doubt. So the real goal of these problems, so I've got my operations off to the side here. I'm going to go ahead and draw a line over here. My goal is actually to end up with the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and then some other values I'm going to call A, B, and C. I'm supposed to end up with something that looks like this. This is the goal. If I can get this, I know x is equal to A, y is equal to B, and z is equal to C. And then I've got my solutions. In order to get it in this step, the operations that you want to first do is I'm going to put the thing in box. I want this thing to happen first. This is the first and foremost and most important thing that I can do. That is hopefully your first step. Step number 1 is aiming towards that. Okay. Now you'll notice here I already have it, so I don't need to worry about getting the 1 in that first corner. After getting the 1 in the first corner, and again, it has to be in this order, after I get this, I'm then going to get the 2 zeros below it. Generally, by getting the 2 zeros below it, it's by using operation C. It's using elimination to say, hey, if I multiply this by a -3 and I add it to this, that thing becomes 0. If I multiply this thing by a +2 and add it to this thing becomes 0. And that's what the second operation would actually be, is operation number 2 is taking row number 1, multiplying it by a +2, so taking this one, multiplying it by 2, adding it to here, so adding that to row number 3, should end up getting a 0 in this position. So that's the idea. Then I'll have 1, 0, 0. My next goal is to get a 1 here, which it looks like I already have, and a 0 here. Again, so I've got first operation, second operation. Now again, when I say that, I shouldn't say it that way. It's the first step of the goal is to get the 1 here. The second step of the goal is to get the 2 zeros here. It doesn't have to match up with the operations and the set steps that you choose to do over here. So after that, our next step is to get the 1 here, and then the 0 below it, and then finally the 1 here. Now, just some additional hint before we move on to the next video where I finish solving this actual problem. This right here, finding this 1 is not absolutely necessary. It's strongly recommended. If I can get the 1 here, then the zeros below it are generally really easy to do. But if I can't figure out nice operations such that I get this thing to be a 1, there might be other ways to do it such that I aim to get zeros here and here, and I can backtrack this to end up being a 1. The same argument is for this one here as well as this one here. If I end up having, say, a 5 here, but zeros in both these positions, then I still know what C is, because I can say 5z equals to c, and I can divide by 5. I still end up able to get the value of what z is. But again, those ones are strongly recommended. The zeros here and here are absolutely necessary. Now I'm going to skip over the concept of these 3 zeros here because there is some operations where you kind of have to deal with them, but we're not going to focus on them simply because we can solve matrices by back substitution after we've got the solution for at least z. Now, just to clarify one more thing about the operations, and I had phrased it down here, but I want to make sure I state it up here. You can take a row and multiply it by a number. It is possible that that number is a fraction. So I don't want to emphasize the fact that you have to multiply by a number here, but you can start implementing fractions into this problem. The reason why I wouldn't recommend it is because by throwing extra fractions into a problem, it might cause some issues with the overall arithmetic of the problem. So let me go ahead and finish this operation right here in the next step, and that'll be your first 2 operations in dealing with this matrix. We'll continue the solving of this matrix in the next video. So the next step here is me taking row number 1, multiplying it by 2. So 2r1 is going to be the same thing as 2, 4, negative 2, 6. I'm going to take row number 3. I'm going to rewrite row number 3 down, negative 2, negative 4, 3, and negative 5. I'm going to go ahead and draw the line here. I'm going to add these things together. This is going to cancel out. These are going to cancel out. Those are just really, really lucky. And then I'm going to get 1 and 1 here. So now I'm going to replace 1 unchanged, because again, that's a temporary modification. The only time that it's permanently modified is when the arrow is pointing at it. So R3 is the only thing that's permanently modified, and that's what this is. So 0, 0, 1, 1 is what goes there. Row 2 is going to go right here. And you know what? I'm just going to go ahead and finish it in this video. Might as well. I see here very clearly that it's 0x plus 0y plus 1z equals to 1. So very obviously z equals to 1. That's my first part of the solution. My next part of the solution is from the second equation. You'll notice I have 0x plus 1y plus 0z equals to 3. Hey, look, now I have my second part of the solution. Now, the idea is that we could now back substitute. We could multiply this thing here by a positive 1 and add it to this row to make that thing 0 and change that value. And I can do the same thing with here, multiplying this row here by a negative 2 and adding it to this row, canceling that out and changing that value. But what I'm going to do instead is I'm just going to get lazy with this. I know that the top equation is 1x plus 2y minus 1z equals to 3. So this is the idea that I'm going to simply, I know what z is, I know what y is, and we plug both those values in. I have 1x plus 2 times my y value is 3, minus 1 times my z value is 1, equals to 3, and therefore I can get x equals, by subtracting 6, I get negative 3. By adding 1, I get positive 4, and therefore x is equal to, that's a negative 6. Subtracting 6 gives me negative 3. Adding 1 gives me negative 2. So I get x equals to negative 2, and therefore my solution appropriately in the x, y, z coordinate system is negative 2, 3, 1. And yes, it is absolutely important that you write it in the correct order. X, Y, Z. So again, those are the 3 operations you're allowed to use in matrices. Those are the only 3 operations, and notice they all row operations, not column operations. And these are the goals that we're headed for: 1, 0, 0, 1, 0, and then 1. And that's how we solve matrices.